Hello, everybody. Yes, I realize I'm the only thing keeping you from beer, and I will promise to do my best. It's been a long sort of conference day, even for me. I was super nervous about going up last, but here we go. I'm super excited to talk to you about data architecture, which is my favorite thing in the world, okay? I know it sounds very weird, but then again, I'm weird. I did arrive here in style since I live in Amsterdam. This is my view this morning as I arrived here. If you need a ride back to the station later, let me know. But this is how we do in Amsterdam, right? We come by boats. But a little bit about myself, otherwise that I love boats. I started out in life as a LAMP developer. Who here was a LAMP developer at some point? Okay, you also aged yourself, 40 plus, welcome. But for the young people, this was like the hottest thing in data, or generally in computing for a while. It's the Linux, Apache, MySQL, and PHP stack, all technologies that, with the exception of Linux maybe, that have seen better days. But I was really excited about the part, the SQL part in LAMP, so much so that this was my actual license plate. I'm not kidding, this was my actual license plate. About 2002. Anyways, the car was the same model, but not much faster. These days, I am a researcher at CWI Database Architectures. I'm a professor of data engineering at Radboud University in Nijmegen, and I'm also the co-founder and CEO of DuckDB Labs. But it has been shortly mentioned, CWI, does that ring a bell for anybody? Does it not ring a bell in Python land? And it should be, because it's right there in your Python shell. If you open Python and you type copyright, you will see this line saying copyright Stichting Mathematisch Centrum Amsterdam. And that is actually the old name for CWI. So it is the same place. It's actually only like 50 meters from my office, where there is a little plaque. I'm also in good company with license plates, because this is Guido's license plate. So he likes license plates too. What can I say? We cannot have these kind of license plates here. It's really annoying, right? We have they're like all structured and nothing. But for those of you who don't know CWI, this is a picture of its beautiful 80s office building. It is a weird place, because you can kind of do your own thing and think about things in a different way. And it's not a university, but it's kind of academic. And I think it's an interesting place in the sense of it leaves you alone enough to do things that maybe other people wouldn't be doing. And actually, at this CWI, we have a little plaque in front of this room where it says the programming language Python was made in this room in the early 90s. And another thing that was made in the CWI is DuckDB. I want to do a little poll. So who here is using DuckDB? Oh my God. Okay, this is something I will continue be doing until I've achieved everyone. So I will have to give talks for a little bit longer, but we went up quite significantly. So thank you that raised your hands, and the others. Let me just briefly tell you what DuckDB is. It is a universal data management, data wrangling tool, if you want, right? It's about data, it's about tabular data, and it speaks SQL. That will not surprise you, given my license plates. And it is the fastest growing data tool, data management system ever, right? So there's these data management systems go back centuries, it feels, not really, 50, 60 years, but DuckDB is the one that's the fastest growing. And it's really interesting, because you've heard from my intro that I am actually a bit of an academic sometimes. But DuckDB really is the answer to the question, what if academic research can actually have impact, right? And basically, we decided that we were going to stop writing research papers for good. It's a very career-destructive move, by the way. And put all our sort of efforts into writing software, in this case, data management software. And it's really interesting to see, and it's worked out fairly well. We have tens of millions of downloads each month, and our website, duckdb.org, is now serving more than a petabyte of traffic each month, which is insane, just for DuckDB-related things. You can ask me over beers later how the ride has been. It's been interesting. DuckDB really loves Python. It's one of the primary APIs, and not just because we come from the same place, but many cutting-edge features actually come to the Python API first. So when we develop something new, it will first be in the core engine, but very quickly we will make a Python binding for it. So one of the things you can do with DuckDB that you cannot do with many other data management systems, some may have copied this idea, is that you can basically, within one Python process, run both DuckDB and the rest of your Python stuff. And that means that you can directly read things like data frames into queries, and you can also directly take the result of queries and put them into a data frame again. And that enables a very different sort of interaction with data management systems. So this works with pandas. That also works with arrow structures. We also works with polar structures. So if you wanted to mix and match, it's not like an all-in thing. You can choose to use it for only one thing. But we're not really here to talk about DuckDB. We're here to talk about data architecture. Okay? So that takes me back a little bit longer to the 1985 data architecture. Okay, so this is what it looks like. We have on the bottom, we have the clients. So these are computers or people maybe. And on top, we have application servers because the clients really cannot be trusted with application code. Okay? And then on top of that, we have the mighty data warehouse because the application servers really cannot be trusted with persistence. And also the clients cannot be trusted with persistence. And there's this interesting sort of structure. Who here has seen this picture before, by the way? Like, this is not that many people. It is actually sort of really the textbook structure of data architecture. Like, if you talk to some consultants, how you should build your data architecture, they will show you something like this, right? It's like very old school thing. And it's super interesting for multiple reasons. First of all, it really puts you in your place if you're in the client level, right? You are not as important as this one thing on top. And it's also really problematic from two other aspects. One is scaling, right? So how many application servers do you need? Unclear, right? Probably more on Christmas than otherwise, but who knows? How big should your data warehouse be? These are questions that I can't answer, and I've been doing this for the last 30 years. So it's really interesting to size these things, and people typically overcommit resources. The other thing I wanted to mention is that these little lines that connect these things are really thin straws. Like, the amount of data that you can sort of pull through those is really limited, and I'm going to go into more details on this. But one of the biggest problems of this architecture, or at least historically, is that you have to deal with the Oracle price list if you want to actually have one of those. And this is the one that I just recently pulled. And so basically the thing with the crown, the data warehouse on top, that's controlled by this very high price equipment. So it's only 1,000 euros per user users per year, or you can spend $50,000 per CPU, which is pretty insane, right? You will get some discounts if you negotiate, but this is the sort of state of the world if you go into that space. And it's actually really great for one guy. So this is an actual picture of Larry Ellison's boat, the guy that founded Oracle. He's one of the richest men in the world. This boat, I looked it up, only 160 million. And that's a low price. This was back in 2011. Today it would be double this. And it's actually built here in the Netherlands, in case you didn't know. We are huge in building the super yachts for the world's billionaires. Bill Gates' new boat is currently in the Amsterdam harbor. Anyways, that was only 600 million, by the way, in case you're wondering. But back to data architectures. You will say, Hannes, you're an idiot. The world has certainly changed since 1985. And this is very true. Are you ready for the change? Are you ready? Okay. Oh! So now we call it the cloud data warehouse. And I'm sorry for Snowflake. with their booth out there. But essentially, nothing has changed, only that we have now moved this whole thing into the cloud. We put the storage for this data warehouse on cloud storage, like S3. And we have some better scaling behavior where essentially the compute of the data warehouse, in this case, these little chip symbols here, are a bit disconnected from the storage. But this is, as the meme goes, it's such wow, right? Like it's not a lot has changed. The fundamental problems still exist, like how do you size these things? The thin straws that you have to suck the data through are still a problem. And that is a bit of a problem, right? Just give a second. So we should change this. Oh yeah, by the way, I want to explain one thing, the thin straw problem. I actually wrote a paper on this, being an academic and all. And this is a fun plot. So by the way, pro tip for academics, plot on the first page. Gets you much higher acceptance rates. It's insane. But here is a plot, and we basically measured how much time it takes to transfer the same table between different databases and the client, right? Okay, so you see these bars here, and you can see MongoDB was particularly bad. DBMSX, by the way, is Oracle. They just love suing people, so they're usually anonymized. But you see that little dashed line there? You see the little dashed line? That is the time if you do the stupidest possible thing and just copy the CSV file from the client to the server, or the other way around, right? And so you can see that these things are criminally incompetent at transferring data, and it might actually be strategic because we call it strategic incompetence, because if you're keeping the data hostage, then you can keep charging them for your superyard purposes. Okay. So the world is pretty bad, but so it's time for some change here, okay? And I'm by no means the first person to say this. And at this point, I want to credit one person. Can you guess which person I want to credit for making the first revolution here? Python and data? Sorry? Widow? Okay, come on. Wes. So Wes McKinney made pandas. And he really is the original revolutionary that took this like data wrangling tech and took it from the gods of Oracle and put it into the hands of everyone, right? I mean, granted, maybe the S language in 1976 preceded it, but that was obscure enough. No, but hi, Wes, by the way, in case you're watching. And this has really been a huge fundamental shift. Like, if you can't really overstate this, how putting data wrangling tech into the hands of everyone has made a huge difference. These days, obviously, some of you may be using Polars, which is the more modern implementation of pandas, the original sort of thing. But it's following the same general design, right? Like give you a way of doing data frames. So we have that. So we have one ingredient of sort of maybe changing the yacht distribution scheme a little bit. The next thing people usually say is, aha, now that you have some data technology, does it scale, right? Will it scale? We need to set some of the, but we kind of want to maybe have our revolution to be a bit more sort of bottom-up, grassroots, so maybe we'll not immediately go for distributed. We'll first see if we have to go for massive scale-out solutions like Spark in the first place. Okay, let's find out. So first of all, again, being a professor of sorts, we'll look at the literature. There's this famous paper here that I can really recommend. It's a couple of years old, from 2015, actually, by Frank McSherry, who, if you don't know him, he's one of these clever people out there. And he basically showed that if you take a sort of a simple algorithm, like in this case, it's a label propagation algorithm, and you basically compare the single thread. Do you see the low line here? Single thread, one core, not many core, one CPU core, single thread. It will take, on this Twitter data set, 150 seconds, and on this UK data set, it will take 400 seconds. And everything else, every big data scale-out system was worse. And why is that? Well, it turns out that a halfway competent single-threaded implementation can beat most distributed systems. And we were aware of this paper, and we were curious how far you can kind of push this. And we thought, well, in reality, most data sets are not going to be that huge, but that was a bit of a guess. But then we were very happy when, I think last year, this data set came out, which is a data set that was published by Redshift. It's a big Amazon SQL as a service thing, and Snowflake, the big data warehouse as a service company. And they basically measured how much data does a typical analysis task, a query, look at in their system. OK. And then on the x-axis, we have the amount of data scanned. On the y-axis, we have the frequency, the distribution, what do you call this, frequency. And the super interesting thing about this plot is, first of all, the median query at the sort of leading big data, large table, whatever, scale-out systems, you looked at 100 megabytes of data, the median. And the crazy thing, in my opinion, is the P99.9 used less than 300 gigabytes of data. Interesting. So a revolution may actually have a chance if we're not immediately jumping to these distributed scale-out solutions. I will tempt the demo gods by doing a demo. OK? So here I have a, so I will have to change this to mirroring. Can you see this? You can see this? And then here I have a shell. Can you read this in the back? Yes. OK, so here I have a data set that is only 265 gigabytes big, right? You can see this. And I'm going to use DuckDB to look at this data. By the way, this data is generated data, so I'm not like leaking anything stuff. This is a standard benchmark called TPCH. And in this benchmark, there's a table. Select. I'm just gonna show you how many rows are in this table, and it's 6 billion rows. It's it's a reasonably sized data set. And now what I'm going to do is I'm going to do something that you will probably be terrified of, which is I'm going to count for one of the columns. Let me just show you this. Select L order key, limit 10. For one of these columns, the order key, I'm going to just count the amount of distinct numbers in this thing. Right? It's 6 billion rows. It's potentially pretty problematic to compute this. And I'm gonna, also to make the task even harder, gonna reduce the memory limit that I have available to do this to 2 gigabytes, because if I use all of the memory in this laptop, it will take too long. Okay? So just 2 gigabytes to read a database that has 256 gigabytes in size to compute a distinct aggregation on a column that has, I will spoil this, a billion distinct values. So I'm just going to run this query. So select count distinct L order key from line item. And now I'm going to, I don't know, run htop here to show you some things. So I'm just going to let this run. And what is amazing about this is that this is an instance of us, DuckDB, running on a data set that is bigger than memory, producing an intermediate result that is way bigger than memory, because the hash table that we have to do to count the distinct numbers here is actually 4 gigabytes large, so it will not fit in memory. But basically, because DuckDB has this feature of going beyond memory for intermediates and input data and output data, actually, this will actually complete, I hope. Don't be stuck. Don't be stuck. Now, I know it will finish. I have faith in DuckDB. There you go. So we just computed distinct on a billion rows in 46 seconds with something that will not fit in the working memory of anything, and it successfully completed. So that's an interesting observation as well. So I'm going to go back to my slides now. I'm sorry. So basically, one of the things we built into DuckDB was this concept that you can go beyond what fits in main memory, which is a limitation of many systems that exist, but basically compute as much fits on your disk, essentially. It's really crazy. And I'm going to show you some interesting experiments. So here's one experiment that we wrote a blog post on. This is a MacBook that I have in my office for my children to watch YouTube on. Okay? It is 13 years old. It was the first MacBook Retina, in case you remember, when it first came out. And I dragged it out of retirement to run data tasks on. It's very unfair. This thing, should be left alone for the remainder of its life. But I was like, no, you go overheat one more. It didn't actually overheat. And it's interesting because we could run the same data size I just showed you here on this modern laptop, billions of rows, about 10 billions of rows, running complex data problems on this. But because of this larger than memory technology and nice scaling over the cores, it could complete all these complex benchmark tasks in minutes, right? And yes, the modern laptop I have here will be faster, but it's pretty insane to think about like a terabyte of data on a 13-year-old laptop. Probably your 13-year-old laptops can't even run a web browser anymore, right? But they can run really serious data crunching tasks. Here's another fun one. This I have to explain. So we thought, okay, maybe we can push a phone, to do these things, and it turns out we can. However, the modern iPhones have this annoying thing that they slow down when they get too hot. So we thought, what if we put it in dry ice? And it turns out, yes, you can also run the same sort of complex benchmarks on a modern phone because they're quite powerful things. And you will see that we have wearing all the required personal protection equipment here, right, when dealing with dry ice. So you can see gloves and masks and everything. Cannot recommend, though, because the phone did die and came back. It came back to life, and then we returned it to Amazon. Anyways, full disclosure. Because I'm not going to use this I'm going to use my phone on it, but I think that was, it's not our proudest moment, perhaps. But the general story here is it's really amazing what with modern data tools, and I'm not only counting DuckDB here. This also includes things like Polars and other tools. They exist. With modern data tools, you can actually push hardware you don't think of, like a Raspberry Pi. We managed to run terabyte-sized data crunching tasks on a Raspberry Pi. We managed to push this laptop. Not this laptop, but a fairly beefy laptop to like 10 terabytes of data. We managed to get this cloud box from Amazon. It's a standard, fairly standard cloud box these days. Put 100 terabytes of data on it. And so this has really changed the world in terms of what I want to tell you is that what you can do on a single computer is insane. Right? You would not believe it if you wouldn't see it. So go try it out. But kind of what this means in our revolution is now that we have everybody's a king, great. So everybody has their own little computer and they have their own little data set, and that's a bit of a problem because we have successfully sort of broken up the monopoly of the the three-layer architecture. We've democratized technology, starting from pandas, but now we've switched to also, in the process, somehow we switched to dealing with files, and there's no more concept of consistency in this picture, right? Everybody has their own little data set. That's not so great. What do we do? So what we do is we think about storage again. And obviously, when somebody says we have to start talk about storage, the obvious answer is just put it on S3, right? So this is kind of in a nutshell what happened when we got the data lakes. We took our little army of kings, of individuals with data sets, and we said, just write it to a file. I mean, there was no kind of governance or anything, so we ended up with the same sort of chaos. It's just that the chaos was now all in one place. Congratulations. So that's not great. What happens if we want to actually collaborate on a data set? What actually happens if we want to enforce some sort of structure on a data set? What happens when we want to update the most fundamental of fundamental things in data sets? What happens then? Well, the answer is we need a lakehouse, okay? This is a lakehouse. And I really hate the fact that now if you Google for lakehouse, instead of finding this, you find some Databricks advertisement. And it makes me really sad, right? So it made me so sad, I went okay, this picture is not as good as it looks like, and in fact it isn't, because here's another perspective on that same house. and there's a gigantic, horrifying hotel behind it. So, when somebody shows you something that looks really good, this is what it's really look like. But let's go back to data. This is just a random rant here. So let's apply some of the same critical thinking, let's say, to lakehouse tech. Let's say you want to put some table on object store. Right? Object stores like S3, they don't understand tables. They just don't. They understand files. What should we do? Well, obviously, we have to just write that table to a CSV file and upload it. I should hear you guys protesting. What should we do instead? Parquet. Yes, we just use a Parquet file. Hey! So in case you're not using Parquet files yet to store tables, I can recommend. It's a binary, compressed, self-describing format for tables. It's really great. So now we have our table. Version 1, we've written it to object store. Great. So now we want to append some rows to this table. What do we do? Anyone? We want to add some rows. Sorry? Another Parquet file. Great, you must be a data engineer. So we'll put another Parquet file next to it. And so now we have basically two files, and then together they form all the rows that are in this table. This is great. And we do that because we don't want to recreate this whole file because it might be a lot of size, big data, whatever. The reading now requires reading multiple files, but we skip over that complexity. So let's say we want to delete from this. This is a bit more complicated because, again, we don't want to rewrite everything. So what we do is we find another file that basically just stores which rows have been deleted, and then basically that we know with the two other files, we know all of that. And that gets pretty messy, so let's just add some metadata structure on top of it to basically keep track of which version was which set of files. And now I have basically, with you, in this talk, in 5 minutes, reinvented Iceberg, okay? So what's really interesting about these lakehouse formats is that they basically give you a way of having some sanity in reasoning about changes of tables that are stored in files and object stores. So going back to our revolutionary sort of file zoo, we now have a bit more sane way to reason about what files are part of tables and so on and so forth. And we also thought about this, and we invented something called Duck Lake. Who here is using Duck Lake? There's one person. OK, I have another task in front of me. This might be harder. So Duck Lake is kind of the DuckDB version of data lakes. In fact, there's a town called Duck Lake in Canada. It has the Battle of Duck Lake Monument. I'm not making this up. We only found this out after naming it Duck Lake, obviously. But this is the town of Duck Lake. Duck Lake is basically saying, instead of all these files, let's just have a database that stores the catalog. And it's really fun to work with, and I shall recommend you working with Duck Lake. So basically, with Duck Lake, we have another way of managing files that are stored in object stores that are sort of somehow cohesive or somehow have to be part of the same table. And I do have a wonderful slide here, because if you want to try out Duck Lake, you can use the very complicated instructions on the screen here. So you have to install DuckDB. That's very easy. That's curl install.duckdb.org. Pipe bash. That's very simple. And then we have to do basically start DuckDB and attach this Duck Lake instance. And it will allow you to basically specify that you will want to store your data on object stores, and you will want to manage the metadata in a Postgres server or something else, and that's going to allow you to basically have all these different computers share a common understanding of what is in a table. So, and I want to kind of go back to this with this famous slide that we now wish we had the guy back. So I saw this on TV. I don't know who else was there, but this is Mr. President Bush basically calling the Iraq War done, famously preemptively. What do you call this? Not preemptively. Prematurely, thank you. So let's go back to our data architecture. We used to have this interesting structure from 1985 where the clients were sort of this wonderful sort of the thing on the bottom, the thing that didn't have anything to say, right? And we had the application servers that had a bit more to say. And again, we had the 2015 update, where now we have Cloud Data Warehouse, and it really didn't change a whole lot. But what's really interesting, if we now think how the 2025 data architecture should look like, because what we can actually do is we can flip this picture. And instead of having clients that are an afterthought and are sort of on the bottom of the stack and are really sort of receiving, the graceful recipients of query results, we can now have devices and users and programs that are empowered in a way. And we can have commodity things like storage and metadata, a bit of a delegation. Like, it's not so important. It's actually on the bottom of the stack. And what does this mean? Well, it's actually very fascinating because there's a lot of stuff that, like, I have seen this Dart data architecture so many times. Like, we have an app, you collect the data in the app, you upload it to the central sort of command, you run something there for every user on their own data that you just uploaded, and then you push that data down again to that user. That doesn't make a ton of sense, right? If you think about it. What we can do instead is, for example, we can say, hey, in this architecture, the data that you create locally stays on your device. We have competent query processing technology on local devices, and we can just run your stuff there. And we have, but at the same time, we don't get this wonderful chaos where everybody has their own version of the data and there's no cohesive sort of thing, because we have this commodity thing like data lake, like Iceberg or Duck Lake formats that allow you to basically use commoditized storage and commoditized metadata structures to communicate about what the state of tables is and maybe what the state of centralized tables is, maybe append to a centralized table after all. And it really changes like the dynamics. For example, one really interesting thing about this architecture is if you have more users, you have more compute. It's insane, right? Like, you're running stuff on local devices. It means if you gain an additional user, that person brings their computer because otherwise they cannot interact with you. Well, if you use that computer for some way of computing things, then you will not have to provision a bigger Redshift cluster, or you don't have to provision a bigger Snowflake cluster, or you don't have to give Databricks more money to query that user, to process that user's data because they're doing it themselves. All you do is maybe charge them. Hey, business model right there. And what's interesting, if you think about it, is that if you think about what made Google possible in the first place, it was that they found a way how to use cheap commodity computers and glue them together with MapReduce to basically enable a business model, which is an advertisement financed search index that wasn't possible before. And now we have this architecture where I don't think we have even figured out yet what the business models are that could be enabled by a data architecture where we're not creating a cloud cost for every additional user, right? Where we're not creating like a liability of data that we now have to manage. And so that's really interesting. And obviously, I don't want to just show you a picture. I also would recommend that you use DuckDB and Duck Lake for these things. But by no means is this exclusive, right? Like, you can, if you want to make me happy for the next talk, more people raise their hand and stuff, that's fine. But there's a bunch of tech out there that can enable this stack, right? And yeah, so in the end, our mission here at DuckDB Labs is to basically give you the confidence to deal with data. That's really all we are about. And I think this kind of architecture of data where we empower the clients has a lot of potential. And we haven't even started to figure out what people can do with. I can give you some examples of what people are doing with DuckDB at the moment to maybe give you some inspiration, right? So here I have a picture of some examples of what people are doing with DuckDB. People are running DuckDB on lambdas, right? So you have a lambda function that runs on maybe next to your data swamp or data lake to process some stuff, maybe on whenever something changes. That is a super crazy use case that you can use with single node, sort of simplistic, simple to use query processing tools like DuckDB and others. People are gluing DuckDB on their application server databases on the left here to basically pre-process their application server data before they ingest into the data lake. That's a huge sort of reduction in cost. You don't have to copy over gigantic text files and then have another task to convert them to something else and then throw them in a Kafka queue. No, no, no. Let's have these servers do this themselves. People run DuckDB on satellites, right? Because it turns out communication to satellites is extremely expensive. If you can process the data locally, you can actually save a lot on this thing. People run DuckDB on cars because cars have all this telemetry. And I don't know if you followed this recent thing where Volkswagen accidentally lost all the telemetries of their electric cars, but like other companies are using DuckDB locally to avoid this. People are using DuckDB on device, in the browser. It's really insane, but I'm not trying to convince you should use DuckDB for this. Again, it would be great if you would, but just rethink the data architecture. It doesn't have to be this triangular sort of top-down thing where you are either paying a cloud provider or you're basically sort of delegated to a child, a client. But it can really, there's a lot of possibilities now, and the ingredients are, competent single-node query engines and, lakehouse formats to basically just basically glue them all together. And yeah, so this is the architecture that I wanna leave you with. Think about what you can do if you maybe start trusting your clients with application code and also the coordination of storage, and try to think of the mighty data warehouse less in the sense of like the almighty data warehouse and more as something that's deconstructed, that's based on open formats that you can access with many tools, that's based on commodity, like a Postgres server you can just rent from anywhere. Cloud storage can rent from anywhere. That's really not the issue anymore. And that kind of really opens up a lot of things and hopefully makes Larry Ellison a little less rich. And with that, I'm happy to take your questions. Thank you.